Okay, so a real quick sound test one more time. Again, guys, if you have any issues with the sound, if things are cutting up, chopping up, do let me know, please. The Discord service is having a problem right now. I'm having trouble connecting to any of the servers, so I can't get any of your messages there. But I am on the calendar page right here. So you can actually send me a message on the calendar, and it's an instant service. I'll immediately receive your message. So if something's unclear as far as the sound goes, do let me know. Um, I've posted the Google Hangout link. So if you want to join the Hangout session so you can ask me questions in real time, do that. Otherwise, you can follow the YouTube stream. So let's start. As I said, this is going to be a calculus class, and we're going to go all the way. I mean, by all the way, of course, I mean we're not going to get into the awesome stuff that I love, the analysis, but we are going to start with basic calculus and then cover differential equations and go into vector calculus, etc. Okay, so this is the book. The book I'm going to be using is by Gilbert Strang, and it's called Calculus, just like this. And the awesome thing about it is that it's completely free, and you can find it on the link. I've posted the link on Discord. The link is the book is hosted by MIT. It's an official link, so that you know that it's completely free. Let's look at the content for a second here. So, Introduction to Calculus. And as you can see, Gilbert Strang does a lot to motivate the subject. So he starts by giving you real life examples of the use of calculus in terms of physics and economics, etc. And that's what this chapter one is. It's introduction. There isn't much actual calculus computation going on here, but there are a lot of motivational examples, which, in my opinion, are absolutely priceless. Chapter 2, derivatives, 3 applications of derivatives. This, I assume, is things like optimization, finding local global extrema. Let's see, Newton's method and chaos, mean value theorem, L'Hopital's rule. We go to chain rule, and then we start integral calculus. The fundamental theorem, numerical integration, absolutely crucial topic you don't see much of these days. Exponentials, logarithms, techniques of integration. So this is things like integration by parts, trig substitution, partial fractions, improper integrals. Applications of integrals. There's a lot of physics here: force, work, energy. If you've done any physics, you know there's a ton of calculus being used here. Mass, moments, probability. A lot of calculus in probability theory. Areas of surfaces of revolutions, volumes of solids of revolutions, length of curves, etc. Polar coordinates. So, absolutely crucial topic is converting between coordinate systems. So, if we're working on a circle, for example, and if our domain of a function are points from a circle inside the disk, polar coordinates are very helpful. They tend to simplify things a lot. So this will come in handy. Let's see here. Actually, someone wrote on Discord, and let me just quickly check what the message is. Will this go over integral and vector calc? Asks Pottle, and the answer is definitely yes. Except it'll take me a little time before we get to vector calc and integral calc, because there are quite a few of you guys, and I cannot assume your prior level of knowledge, so I need to start at some base level. And I would just rather start from the beginning. So yes, we will cover vector calculus, and then after we're done with this, this is a personal project of mine. I actually need to improve my own understanding of things for work that I do, for the research that I do. So I definitely plan on eventually going into analysis, etc. So yeah, we will be going, as much as we can, as far as we can. Infinite Series, Chapter 10. I love this stuff. This is bread and butter. And actually, there's a great book called Calculus. What is it called? Calculus, a historical approach, I believe it's called. And it actually presents the subject as it was discovered by Newton and Leibniz. And they actually started with, I don't know if they started with infinite series, but it is one of the first topics in the book. So they definitely considered series as a foundation for how calculus came to be. Chapter 11, this is where we get into vectors. So vector calc's coming in. Matrices are very helpful when doing vector calc. This is another thing you don't quite often see in college level calculus courses. They tend to separate vector calc and linear algebra. And this is kind of a disservice, because linear algebra, if you can work with matrices, when you have vector valued functions, so your total derivatives are sometimes represented as matrices. And if you know how to work with matrices, this can be very helpful, save a lot of time. Okay, motion along a curve. So there's some physics here. Partial derivatives, multiple integrals, vector calc. There it is. So Stokes' theorem, Green's theorem, surface integrals, divergence theorem, the good stuff. And mathematics after calc. So this is linear algebra, which we're already doing, both computational and theoretical. So DiffEqs, discrete math, which we'll be covering in the data structures course. I don't plan on going easy on the math and data structures series. So let's get into it. Let's see. So we start here. Introduction to calc. Okay, so Strang starts by motivating the subject in terms of velocity and distance. And if you look here, he presents an odometer as an example. So let's give this a read. The right way to begin a calculus book is with calculus. So this chapter jumps directly into two problems that the subject was invented to solve. Okay, so immediately Strang tells us that we have two problems. These are two main questions we try to address with this whole subject. So we begin with an example that is familiar to everybody who drives a car. It is calculus in action. The driver sees it happening. The example is the relation between speedometer and the odometer. So if you're not familiar with these words, speedometer tells you what your speed at any given point in time is. What speed you're driving at, 60 miles an hour, 55 miles an hour. The odometer tells you how many miles you've traveled. Okay, so suppose as one particular example, you may be driving 60 miles per hour right now, and so far you've accumulated, let's say, 70,000 miles. So that's what the speedometer and the odometer would tell you, respectively. So one measures the speed or velocity, and the other measures the distance traveled. There we go. So we will write v for velocity, and we will write f for how far the car has gone. Okay, so the two instruments sit together on the dashboard. If you look at this picture, we have v equals 55 right here, and f equals 1,991. So that's how many miles we've traveled. That's the speed we're at right now. Notice that the units of measurement are different for v and f. The distance f is measured in kilometers or miles. So right away, I'm going to say I just don't even acknowledge miles or inches or feet as units. It's absolutely ridiculous to me, and we're just going to stick to the metric system, okay? So in kilometers, the velocity v is measured in terms of kilometers per hour. Okay, so currently, if you look at this image, our velocity is 55 kilometers per hour. For every hour of travel, I cover 55 kilometers. Okay. The unit of time enters the velocity, but not the distance. Every formula to compute velocity from f will have f divided by time. Okay, and here's in bold, the central question of calculus is the relation between v and f. So this is, you should definitely think about this. So he says the central question of calculus is the relationship between these two functions. The function that gives you information at this point in time, that's our velocity, that's our total distance over time, and the total distance, and f, which is the total distance we've covered so far. Okay, starting from the beginning, maybe, up to this point. And the relationship between these two questions is the central question of calculus, the relationship between these two functions. Here is the first question. Can you find v if you know f? So if I tell you, you've covered, at this point in time, we pause time right now, and I ask you, you've covered 30,000 miles. Can you tell me what your velocity is? And vice versa. If I tell you what your velocity is, maybe at each point in time, I tell you at time 0, at time 1, your velocity was this much. At time 2, your velocity was this much. 3, this much. and I ask you, how much distance have you covered in total? In other words, what is F? Can you answer that question? So this relationship is central. If we know the velocity over the whole history of the car, we should be able to compute the total distance traveled. So this is intuitive. In other words, if the speedometer record is complete, but the odometer is missing, its information could be recovered. One way to do it without calculus is to put in a new odometer and drive the car all over again at the right speeds. So that seems like a hard way. Calculus may be easier, but the point is that the information is there. If we know everything about velocity, there must be a method to find F. Okay, this is absolutely crucial. So he says this F, the information is, this function is recoverable if I know the velocity at any point in time, at every point in time. So what happens in the opposite direction when F is known? If you have a complete record of the distance traveled, could you recover the complete velocity record? Okay. In principle, you could drive the car, repeat the history, and read off the speed, right? You're driving the car, and you're reading off what your speed is, and you're recording it at any moment in time. And the reason is because you know F. So at any moment, you know how much distance you've covered, so you travel at the required speed to match that information. So that at time 1, you've covered this much distance. At time 2, you've covered this much distance. So you adjust your speed accordingly, and you just record what your speed is. But again, you can imagine it's ridiculously tedious, probably even like impossible, so there must be a better way. So the whole subject of calculus is built on the relation between these two functions. There you go. Right away, Gilbert-Strang just gives you in one line, in my opinion, the crux of the subject that will completely be unknown to you if you're reading about calculus from a theoretical book. So first presentation to the topic in my subject, in my opinion, should be from an application-based book like this. Let me quickly check the calendar, see if anyone, let's see, has any questions. It appears Discord is down. How will we approach the interaction of the part lecture? Okay, let me just post the link to folks here. And okay, so there it is. Let's continue. So we go back to the book here. The question we are raising here is not some kind of joke, after which the book will get serious and the mathematics will get started. On the contrary, I'm serious now, and the mathematics has already started. So this is awesome. Strang tells you this is not some hand waving that I'm doing, and then the mathematics will be revealed to you in like 10 chapters. We've started calculus already. Talking about the relationship between these two functions is what calculus really is. So we need to know how to find the velocity from a record of the distance. This is called differentiation. So we will talk about derivatives and differentiation and differential calculus. And what that is finding information about velocity from a record of the distance. We will also want to compute the distance from a history of the velocity. And that is integration. So that's the opposite side, right? I want to compute the distance if I have record of the velocity function. And this is integration, and it's the goal of what we'll call integral calculus. I won't be using this terminology, differential calc and integral calc, because I just don't believe that there should be a split between these things. It's one subject, really. These things are very much tied. I'm just going to call it calculus and differentiation and integration. So differentiation goes from f to v. Integration goes from v to f. We look first at examples in which these pairs can be computed and understood. So let's look at these examples here. Let's look at these examples. Constant velocity. You're in a car, okay? I'm in my car. I'm driving at some constant velocity, and suppose the velocity is fixed at 60. I just refuse to use the word miles. 60 kilometers per hour. Okay, then f increases at this constant rate. What is f again? F is the distance we've traveled, right? So if my speed is 60 kilometers per hour, this is the rate at which my distance increases. After 1 hour, how far have I traveled? 60. After 2 hours, 120. After 3 hours, 180, and so on. So for every hour, we add 60 kilometers. After 4 hours, right? So you do 4 times 60, that's 240. Okay, can we catch a relationship here? So let's go here. Let's try to write this down. So we're going at a constant velocity. Their velocity was our v function, right? So the velocity after 1 hour, I'll just write, our velocity is actually constant. So velocity is 60 kilometers per hour. Okay, so if I travel for 1 hour, how far have I traveled? Where for every hour I travel 60 kilometers. So that's 60 kilometers. What if I travel 2 hours? Well, that's 1 hour more. That's another 60. 3 hours. That's another 60. And notice the relationship here. 1 times 60 is 60. 2 times 60, 120. 3 times 60, 180. So if you tell me how far have I traveled after some t hours, some any time you want, some t hours, what do? I multiply 60 by t. And there is my function describing what the odometer would tell you, right? The distance you've traveled. We've recovered this information from the information about our velocity. This was the central question of calculus, right? And this is a line, of course, we can graph it. It's the line that passes through the origin, and it has slope 60. 60, there we go. All right, we move forward. We say f increases linearly with time. Its graph is a straight line, right? So we just drew this f, 60t. There's our function. And on the left, you see the function of the velocity. And I'll just graph it here. For the sake of completeness, velocity is constant. It's 60. And we, of course, know that constants are horizontal lines like so. And it has a y-intercept of 60. That's my velocity. V of t is the constant 60. So also notice that this is my origin. I've drawn a line. Part of the line is to the left of the origin. So of course, time can't be negative. The x-axis is time, and this technically doesn't exist, but it's a line, so I just draw it for continuity. You can ignore this left portion of the line. All right. Moving on. Notice that this example starts the car at full velocity. So at time 0 at the origin, your velocity is immediately 60. You don't accelerate, you don't get to 60, you just start there. No time is spent picking up the speed. Notice also that the distance starts at 0. I mean, if you look at the graph right next to it, the distance starts at 0. So that makes sense because you haven't covered any distance yet. You were stopped. Those decisions make the graphs of v and f as neat as possible. One is the horizontal line, the other is the sloping line, f equals 60t. This v, f, and t relation needs algebra, but not calculus, right? 60t, the way we recovered f from v, there was no calculus there. We just did algebra. So, hence, we can make this statement. We can say if v is constant and f starts at 0, then f equals v times t. Right there, you just answered a calculus question. You recovered your odometer information from your velocity information. And what we just saw is that if your velocity is constant, like it is here, then my function f will be that velocity times time. If we start from the origin, if we start at 0, right? Now, you could have started somewhere else. You could have said this. Look, you could have said, here is, for example, a road, and this is where the road starts. We'll call this our origin. But suppose my car was parked a little further. It was parked, whoops, the stylus isn't the best. So it was parked 3 meters down the road. So this distance here is 3. And now the car starts moving at at 60 kilometers per hour. So what is my function? What is my f? It's going to be very similar to the f before, except we started 3 meters down the road, and so instead of the function we had before, we now have this function. So 3 meters above the origin, there it is, f of t equals 60t plus 3. So our y-intercept is all that changes. But again, we have a line. All right. So moving on, the opposite is also true. When f increases linearly, the velocity is constant. And that makes sense, right? If the distance you travel is increasing linearly, then you're traveling at a constant velocity, because if you weren't traveling at a constant velocity, the distance you covered between certain time intervals, between fixed time intervals, would be different. In the first hour, you'd cover some distance. In the second hour, you'd cover a different distance because your velocity was changing. If the distances you cover at each interval of time are the same, then your velocity is constant. So division by time gives me the slope. What? So let's look at that. If you have f equals vt and you divide both sides of the equation by t, what are you left with? You're left with your slope, right? In other words, your slope is your velocity. Let's go back to this graph. Let's go back to our simple case. There it is. So if I take this function here, I see that my slope is 60. And how do I get the 60? I divide both sides by t, and I'm just left with the 60, and that's what we call slope. So this right here is my m. That's what we call it in algebra, right? Usually, slope, m. All right. Let's see. The distance is f1 equals 120 miles when time is 2 hours. Well, if you plug in 2 into t, v was 60, you get 120. Now, when t is 4, of course, f is 140. At both points, the ratio is 60. Okay, I want to graph this. Again, this is all review. We start with a review. So, bear with me, but this is important information for what's to come, so I'll cover it. We have this function that we've recovered from our velocity. If we had velocity equals 60. We were also told that the car starts at the origin. From this, we recovered our odometer function. Now, we plug in a couple points. We say f when time equals 1. If I plug in 1, I'm 60 kilometers down the road. What is the reading of the odometer when time is 2? Well, it's 2 times. That's 120. Now, what is the ratio? What is the ratio? The ratio is, of course, if I take this and divide by this, what do I get? I get 2, right? Now, if I wanted to know what the slope was, how do we find the slope? f2 minus f1 divided by the time difference, which is 2 minus 1 is, of course, 1, and we get 60. The slope is 60. Fine. What would be my position at time 3? That's 3 times 60. That's 180. And finally, at time 4, that would be 240. Now, I want to make sure that this is a line, and I ask myself, can I find the slope between these 2 points? So again, we do 240 minus 180. The time difference between them is, again, 1 hour. So that's 1. And that's, of course, again, 60. So we see the same slope here. And this 60 is, of course, our velocity. All right, so our velocity tells us what the slope is of that line, of this line over here. Okay. Velocity and distance, 1.1. Let's see. So we have a couple graphs here. Let's take a look. The right graph, f equals 20 plus 60t. So this is a line. The y-intercept is 20. So we can assume the car no longer starts at the origin, but starts 20 kilometers down the road. It's traveling at 60 kilometers per hour. We see the v function on the left here. It's the constant 60. Let's give this a read. The distance starts at 20 instead of 0. So we just established that. The distance formula changes from 60t to 20 plus 60t. Okay, that we also established. The number 20 cancels when you compute change in distance. So the slope is still 60. How does that work? Okay, when you compute change in distance, so suppose I now have this function. F of t equals 20 plus 60t. And I want to know what the slope is. Strang just said 20 cancels. What does that mean? Well, let's take 2 points. I say, what is the odometer reading after 2 hours? Well, I plug in 2. 2 times 60, 120 plus 20, right? That's 140. So the calculation is this, 20 plus 60 times 2. Fine. What about at time 3? At time 3, we get 200. And how do we get 200? Well, we do 20 plus 60 times 3. So now you want to know the slope. So how do we find slope? F of the later time, this expression. So let's go down, zoom out. All right. So 20 plus 60 times 3 minus 20 times 20 plus, in parentheses, of course, 60 times 2 over 3 minus 2, which is 1. And you can see that if you distribute the negative sign, 20 minus 20 cancel, and you're left with 60 times 3 minus 60 times 2, which is 180 minus 120, which is 60. So the slope is still the same, irrespective of your starting position, which makes sense. It doesn't matter if you start at the beginning of the road or 20 miles down the road, you're still traveling at 60 miles per hour. When v is negative, the graph of f goes downward. Okay, the car goes backward, and the slope of f is negative 30t. Okay, so if you look at this dashed line here, you see the graph of the function is going down. The values are negative, and the slope is negative 30. And if you look at the left graph, you see v equals negative 30. This makes complete sense because at this point, the car decides to go backwards. Maybe stops, turns around, and he's going backwards. We have to establish some kind of convention. Which way is positive values? Which way is negative values? Let's assume going leftward if you're an observer from the side, if you're observing the car from the side. Let's assume if the car goes left, we'll establish those values as negative. So v equals negative 30, the car goes back, and that's why the distance traveled becomes negative, right? You're traveling the other direction now. And Strang says this. He says, I don't think speedometers go below 0, but driving backwards, it's not that safe to watch. If you go fast enough, Toyota says they measure absolute values. The speedometer reads plus 30 when the velocity is negative 30. So if you've covered vectors, if you learned about vectors in maybe high school physics, you know that mainly the difference between velocity and speed is that velocity also, it tells you the direction. It's a vector, whereas speed is a scalar. So even though your speed is still 30 miles per hour, you're traveling in the opposite direction, hence the negative sign. All right. Velocity versus distance. Slope versus area. Let's see. How do you compute f from v? So in other words, the thing that we just did in our heads right here, let's go up. We were given v was 60, and we figured out that f is 60t. How do you do that? If v is more complicated, for example, you might not be able to guess, right? What's the process that your brain goes through? The point of the question is to see that f equals vt, to see f equals vt on the graphs. We want to start with the graph of v and discover the graph of f. Okay, so that's how we're going to do this. We're going to, if I'm given velocity, I'm going to graph it. And then using that graph, I'm going to try and discover the graph of the function f. Amazingly, the opposite of slope is area. So what was slope again? Slope, we said, was v, the velocity. Now he says the opposite of slope, the opposite, the slope. What was the opposite of the v? Well, it was f, right? That was the whole discussion here. They're related by this. So the opposite of v, in other words, my f, is the area. What does it mean? Let's see. The distance f is the area under the v graph. So right there. Let's go here. Let's go below. Let's do some examples. So if I give you a car that's again traveling at a constant velocity, like so. Let's say v of t is 30 kilometers per hour. And let's stop at time 3 hours, for example. Okay, I'm interested in this portion. And I tell you what is the distance the car has traveled in this time frame from time 0 to time 3. So what Strang just said is that the opposite of velocity, which is our odometer reading, our function, is the area under the velocity curve. That's it. That's how we were able to find f from v. And when the function is constant, when our velocity v is a constant like this, finding the area becomes simple. It's a simple geometry question. What kind of shape is this? It's a rectangle. How do I find area of rectangle? I do height times base. What is the base? It's 3, right? And what is the height? Well, the height is 30. So I do 3 times 30. That is the area of this rectangle, and that is 90. So how many kilometers have I covered after 3 hours? I've covered 90 kilometers. Okay, fine. What about after 4 hours? What if I stopped my car here? Well, then you'd have this rectangle, this larger rectangle. Notice the height is still 30. The only thing that changes is the base. It's now 4. So you would do 4 times 30, and you get 120 kilometers. All right, let's generalize this question. What if I stop the car at some time t star? Okay, and I said how much distance have I traveled? What is my odometer saying? So now you have this longer rectangle. What is its area? The height is still 30. What is its base? T star. Well, f of t star is 30 times t star. There you go. Now I've recovered my odometer function from my constant velocity function. What did I do? I multiplied the velocity by the height because that was the area under the velocity curve. So that is the crucial piece of information right there. The way we find f. So basically, I'm just going to write this out in my own words. To find f from v, okay, compute the area under the v graph. Okay, back to the book. The distance f is the area under the v graph. Okay, when v is constant, the region under the graph is a rectangle. We just saw this. Its height is v, its width is t, and the area is their product. We just did this example. This is integration. To go from v to f by computing the area. So right there, you ask yourself, what is integration really? What is an integral? Well, when we do integration, we do this. Okay, given the velocity function, we find the area under it to find the f, to find our odometer reading. That's integration. Now the other way. The slope of the f graph gives the velocity, the v function. Okay? This is the crucial relationship. See, the slope of f gives me v. The area under v gives me f. So the area under v we just saw. Here it was. We had the v. We looked at the area. We got f. And over here, we had f. We looked at the slope, and we got v, 60. So this is the relationship. Integration is finding the area under the v graph. Okay, so there's integration. And differentiation is the other way. Given the function, we find the slope. Okay, we find the velocity. And that's differentiation. All right, let's go to the example, forward and backward. Let's see what this example is. Let me take a quick sip of water. Actually, talking while you're trying to read the book, you'll quickly realize your voice just disappears. So, all right. There is a motion that you will understand right away. The car goes forward with velocity v and comes back at the same speed. To say it more correctly, the velocity in the second part is negative v. All right, let me just draw this out. When I read something like this, math books in general, I actually like to draw this out. It helps me visualize stuff. So we have a car. We start at some point. We'll call this our origin. We go to the right with velocity v. And then we go back here with velocity negative v, and we end up where we started, at the origin. If the forward part lasts until t equals 3, so let's say it takes 3 hours to get to the end of the forward part, and the backward part continues to t equals 6, the car will come back where it started. So, I mean, think about this. If you're traveling at a constant speed, it takes you 3 hours to get to this end of the right motion. So to this end, took you 3 hours. And then it takes you 3 more hours to get back here. Right? It should take you 3 more hours if your velocity is not changing. Notice this velocity is not changing. It's still v. It's the direction that's changing. But the speed is still the same. So if it took him 3 hours to get here, and if he's going to turn around and travel at the same speed, then after 3 hours, he'll end up where he started. Okay. So the total distance after both parts will be f equals 0. So what is the distance, the total distance after both parts? Okay. The total distance after both parts will be f equals 0. So what does it mean the total distance after both parts will be equal to f equals 0? This graph explains it the best. So looks like the left graph. The left, give me a second. Let me look at the calendar again. No messages, I believe. Yeah, so I'm assuming everyone can hear me. Okay, so the V graph here, 3 hours, you see the positive V, that's his speed. And look at the area, 3v. And we just said that the total distance traveled is going to be the area in this rectangle. So that's the distance he's traveled, 3v. Then at time t equals 3, he turns around and he starts traveling at the speed v, but in the opposite direction. And he travels for 3 more hours. And of course, the area here is like negative 3v. It's sort of below the x-axis. And here's the distance function, right? So here is our distance. The distance traveled was the area, 3v. So that height right there has to be 3v. He starts off, he goes up. Our slope is v. There's the slope, he goes up, he turns around. Now, when he turns around, he's going in the opposite direction, right? And we established that if you go in the opposite direction, your f values are negative. So they start decreasing. Your v is negative. So you start decreasing, and then you hit 0. So if you ask me, what is your displacement, right? How much have you been displaced? After 6 hours, the answer is 0. I haven't been displaced. I started at the origin, I ended at the origin because I turned around and came back. So what this tells us really is that f doesn't necessarily measure the total distance traveled, but it rather measures the difference, right? The displacement, where we were and where we are at the end of our travels, where we started from and where we ended. In this example, we started at the origin, we ended at the origin. So f is 0 here. Okay, notice that this means that the total area under the V graph is 0. If you look at this area is positive 3v, this area is negative 3v. And I know you may be saying that areas can't be negative, but v is negative here, so we multiply, we get negative 3v. And if you add them, they cancel. The total area at time 6 is 0. And we know that the odometer reading is the total area under the V graph. So if that's 0, then the odometer should be reading that the total displacement should be 0, which is what it is at time 6, as we see on the right graph here. Okay. So A negative velocity makes the distance go downward with a negative slope. The car is moving backward. Area below the axis in the V graph is counted as negative. So this is going to be important when we start doing integration. Area below the x-axis in this V graph is counted as negative. Now we go to functions. So this forward back example gives practice with a crucially important idea, the concept of a function. We seize this golden opportunity to explain functions. What is a function? So the number v of t is the value of the function v at time t. So you have some velocity function, and then you ask the function, what is your value at time t? And out comes a number, and we call that number v of t. Okay, t is the input into our function. The velocity at that time is the output of that function. Most people say v of t when they read this v parentheses t. The number v of 2 is the velocity when t equals 2. Okay, so this should be relatively clear. Now, here is a v function. This is the forward-backward motion we just saw converted into a function form. So we say v of t is going to be positive v if time is between 0 and 3. Then at time 3, we turned around, right? So at that point, it's going to be negative 3. Now, what is the velocity at the instant when t equals 3? I mean, if you think about it, if you're moving forward, and then after 3 hours you want to turn around, well, you can't just turn around, right? You need to, if you're moving in single dimension, you actually have to stop before you can turn around and go back. So if your velocity all the way to this point is v, you're not even slowing down, it's just constant. What happens at that point? Is your velocity 0? Does the first hit 0, then continue at negative v backwards? So it's kind of unclear, and that's why it's a question mark. And this is what we'll call later possible discontinuity point. For now, that term might not make sense. So it's unclear. So there's the question mark. The input t is converted into the output plus v or minus v, and the velocity depends on t. So right here, Strang goes on to say, in the case of this function, at time equals 3, we have the function is discontinuous. What does that mean? It means the needle of your speedometer jumps at that point. It jumps from positive v to negative v. So the velocity is not defined at that instance. There is no v of 3. In real life, things don't work that way. Well, at least in cars, right? You have to slow down first. The graph of f has a corner, and we can't give it slope. What does that mean? The graph has a corner here. Well, if you think about the fact that v of let's graph these things so we can visualize how this works. We have the following function. We have velocity equals positive v when time is between 0 and 3, and negative v after time 3 all the way to time 6. And at time 3, we don't know what's going on, right? Well, let's see. Let's graph the odometer function. Let's graph the f based on this information. Well, let's just say our car started at the origin. Now, all the way up to time equals 3, we had the velocity positive v. So we know how to graph this, right? We went up with slope positive v. There we are, positive v slope. After time 3, we go down with negative v slope. So we going down like this. And notice that our f graph is essentially an absolute value function turned upside down. And at this point, we have an open circle. That's this undefined part. We have an open circle. Now, notice that if I ask you, what is the slope at point 3? Well, is it positive v or is it negative v? Which one do you use? Which of these lines are you going to use to tell me the slope at this point? Right? If you approach from the left, the slope is positive v. If you approach from the right, the slope is negative v. So they don't seem to converge to some common point. That's why we say the slope at this point does not exist, and we call this discontinuity. Okay, so that's the sharp corner Strang is talking about. This is, of course, our f function, our odometer displacement. All right, the problem also involves the second function, the distance. And this is exactly the graph we just did, right? This is the v of t between 0 and 3. This is this line. Here it is, v of t, vt. And then here is the second line. This is the line that's upside down and it goes down. At the switching time, the right side gives two instructions. This would be bad, except that they agree f3 equals 3v. The distance function is, in fact, continuous. There is no jump in f. Okay, so after t equals 3, the distance decreases because of negative vt. So if we look here, after t equals 3, our distance starts to decrease because we have negative slope. All right, now part of knowing f is knowing all its inputs and outputs, its domain and range. So as part of this review, here's the terminology. Functions have domains and ranges. What is a domain? The domain of a function is the set of its inputs. The range is the set of its outputs. So if we come back here, you ask yourself, what are the possible inputs to my function? These t values, what can I plug in? Well, if t is time, maybe your inputs would be, say, from 0 to positive infinity, or in this case, maybe from 0 to 6. That would be your input. And then what could be your output? What is the highest you could ever be here? Well, the highest you could ever be would be what if I were to plug in 3 here, I would get 3v, right? 3v. This height is 3v. And the smallest displacement here, if I stop at time 6, is of course 0. I'm never falling below the x-axis, so my range, my possible outputs are from 0 to 3v. So that's inputs and outputs of a function. And here we see that 0 to 3v is my range, 0 to 6 is my domain. Summary. More about functions. Let's see what Strang says. May I collect together the ideas brought out by this example? We had two functions, v and f. One was velocity, one was distance. Each function had a domain and a range, and most important, a graph. For the f graph, and remember, velocity is v, f is our odometer, right, in our analogy. For the f graph, we studied the slope, which agreed with our velocity. So the slope of our f graph agreed with our velocity. For the v graph, we studied the area, which agreed with our f. Calculus produces functions in pairs, and the best thing a book can do early is to show you more of them. All right. So we have in goes our input time. It goes through our function f, and out comes a number, f of t. In goes an input, let's say 2, into our velocity function. Out comes the velocity. Okay, so domain range. This shows you the relationship between domain range. Domain is the things you put in. The things that come out are part of your range. Note about the definition of a function. The idea behind the symbol f of t is absolutely crucial to mathematics. Words don't do it justice. By definition, a function is a rule that assigns one member of the range to each member of the domain. All right, so that I feel requires some explanation. Let's see. Let me go here. So sometimes we will see that. Let me do an example here. Let's make a function. Let's draw out a line. Here's a line. F of t equals 3 plus t. This is a line, of course, slope is 1, y-intercept is 3. Now, if you start plugging in values to t, what do we get here? We get, let's say, f of 0 is 3. F of 1 is 4. F of, if we assume we can plug in negative values for t, of course, f of negative 1 will be 2, etc. And you see that what we get here are, we can represent this whole information as a pair of numbers. The first pair will be t. This will be coming from our domain. These are the things I just plugged in, right? The 0, the 1, the negative 1. The second number in this pair will be our result, the thing in the range, the f that comes out. So this will be our range. Okay, so we can think of a function in terms of these pairs. And what Strang is saying is that a function is a rule that assigns one member of the range to each member in the domain. So he says that when you plug in something from the domain, in other words, this t, you automatically get a member of the range assigned to that t. And we see that here. Here's our thing from the domain, t. Here's our member of the range, f of t, assigned to it. And so if we look at all of these pairs, for let me write this down, all these pairs for all t's in the domain, this is our function, right? For every t in our domain, I form a set of all these pairs, the t and the member of the range assigned to it. This becomes my function. So this specific function has members 0, 3, right? Here it is, 0, 3. Input was 0, output was 3. 1, 4, -1, 2, etc. And if I were to plug in all the members of my domain, and I look at all this set, I have my function. Everything about my function is described right here. So that's what Strang says. Now, in practice, what matters is the active part. The number f of t is produced from the number t. We read a graph, plug into a formula, solve an equation, run a computer program. The input t is mapped to the output f of t, which changes as t changes, right? So as you change what your t is, what your input is, your f of t will also change. Now, calculus is about the rate of change. So what does that mean? That means, okay, when I change my t, the thing from the domain, the 0, the 1, the -1, when I change it a little bit, how quickly does by how much does my f change? So if I take this specific example right here, 0, 3, and now instead of 0, I say 0 0.00, let's say 0 0.001, okay? What will be my f of 0 0.01? Will this be huge? Will this be much different than 3? Or will this be close to 3? Right? Because 0 0.01 is where it is close to 0. So you might intuitively say, well, if the input is close to the 0, the output should also be close to 3. But that's what calculus is all about. What is that rate of change? If I change my input slightly, does my output change slightly, or does it change by a huge amount? And that's, of course, what our slope tells us. Okay. And this rate is our function v. That is what our function v tells us. That is our velocity function, right? So for example, here we have f of t equals 2t plus 1. Let's write that down. Let me go over here. Let me erase this stuff. Okay, so f of t equals 2t plus 1. And now you say, okay, what happens if I increase my time by 1 hour? So suppose now I plug in f of t plus 1. So what happens? 2 times t plus 1 plus 1. We distribute the 2 in. We get 2t plus 3. What is the difference between this expression and this expression? Well, the difference, the f of t plus 1 minus f of t, this difference is, of course, 2. So when I changed my hour by 1, my distance covered increased by 2. And where do I find this information? I find this information in the slope of the line, which was, of course, my v of t. So v of t tells me this rate of change. Okay, for lines, this is our slope. All right, let's move a little down. Let's see. A graphing calculator also moves the graph. This is not crucial here. There are two basic ways to change a function. Instead of subtracting or adding, we can multiply the distance by 2. Actually, you know what? I want to read this part. This is about moving functions left, right, up, and down. But the way Strang talks about this is, in my opinion, very on an intuitive level. So I want to make sure we discuss this. So, okay, here's f of t equals 2t plus 1. Now, it is quite hard at the beginning and not automatic to see the difference between f of t minus 2 and f of t minus 2. So if I take whatever my function is and I subtract 2 from it, he says it's very different than when I take my function and just plug in t minus 2. Those are both new functions created out of the original function. In the first one, we subtract 2 from all the distances. That moves the whole graph down. So let's go over that. Let's see that in action. Getting rid of this here. All right, so I have f of t minus 2. This is my new function. Let's just call it something. Let's call it g of t here. What was f of t? F of t is right here, 2t plus 1. Let me graph that. 2t plus 1, small graph right here. Here's my 1 y-intercept. There it is, 2t plus 1. Now g of t is that minus 2. What does that mean? That means for every value that I have on the line, decrease that value by 2. Bring it down 2 units. So this point, the y-intercept, that was at height 1. If I bring it down 2 units, where does it end up? If I bring it down 1, I go to 0. I go down 1 more, I go to -1. So my new y-intercept is -1. And that happens to every point on this line. And so my whole line ends up looking something like this. And essentially, you can see that we've brought the line down by 2 points, right? Brought the line down, the minus sign, by 2. That's what that does. What about this one? F of t minus 2. So if you're a bit unsure about how to figure this out, plug in points. There's no shame in plugging in some points. So we have the graph of f. There it is. Now, I know that in f, when I plug in 0, I get 1. What happens if I plug in 0 here? If I plug in 0, I get f of minus 2. What is f of minus 2? Well, if I plug in minus 2 for f right here, if I plug in minus 2, 2 times minus 2 is minus 4. Minus 4 plus 1, minus 3. So I'm getting minus 3. If I plug in 0, I got minus 3. 1, 2, 3 down right there, minus 3. What happens if I plug in 2? Well, if I plug in 2, I get 2 minus 2, that's 0. What is f of 0? F of 0 is, of course, 1. So f of 0, if I plug in 2, we just got 1. So 1, 2, 1, right there. And my line now will look something like this. Okay, and what this constitutes is the following. Notice this point right here in our f function, our y-intercept. That point is now right here. What happened to that point? Well, it was our y-intercept, right? It was the output when the input was 0. Now we have that 1 when the input is 2. So what happened is our whole line got shifted right by 2 points. So when we have this minus 2 in the parentheses, we're shifting our function right by 2 points here. So there is a difference. Here we shift down 2, here we shift right 2. They're new functions, they're different functions. All right. Now, moving on, let's see. There are 2 more basic ways a function can change. Instead of subtracting or adding, we can multiply the distance by 2. What does that mean? Multiply the distance by 2. Let me get rid of this stuff. So my distance, I'm going to make up a new distance function, or let me just write one. F of t equals 3 minus t. Here's my distance function. Oh, let's do 3 plus t. Here's my distance function. Now it says you can multiply it by a number. Okay, let me make this new function that is 2 times my previous one. what does that become? F of t was, of course, this expression. So that's 3 plus t. We distribute. We get 6 plus 2t. Let's graph these and compare. 3 plus t. This is a line with slope 1, y-intercept 3. Suppose that's my line. Here's 6 plus 2t. So we're 1, 2, 3, 4, 5, 6, etc. So this is our 6. Our slope is steeper, twice as much. Let's suppose this is my line. Now, how can you explain to yourself this transition here? What happened to this original line to get this line? Well, what happened is that, what did we do to the original line? Well, look at this expression. What did we do? We multiplied literally every value on that line by 2. So if you take this value here and multiply it by 2, what happens? Well, it shoots up, right? We're multiplying by 2, it becomes higher. Well, if every point here is going higher and higher and higher and higher, that accounts for the steeper slope. That's why the slope becomes steeper, right? If this point is, if the x-coordinate is 2, suppose, or let's say it's 1. If the x-coordinate is 1, 1 plus 3 is 4. This would be the point 4. When I multiply 2, that point becomes 8. When the x-coordinate is 2, we get 2 plus 3, that's a 5. That's a 5. When I multiply it by 2, we get 10. So we went from 8 to 10. And so you can see this line becomes steeper. And it's the same on the negative side, right? If I were to plug in some value and I would get a negative here on my line, after I multiplied by 2, I get an even more negative value down there. And again, that accounts for the steepness in the negative section as well. So that's multiplication by the function. And another way we can modify the function is we can multiply the t inside the parentheses. So we can make this new function and let this be f of, let's say, what? Let's do half of t. F of t. What does this do to my f? How does this transform my original function? Get rid of this part. So again, if you can't visualize this immediately, or you're unsure, plug in some points and compare the graphs. The graphs of functions are very, very helpful tools. So I try to plug in 0 first. 0 is always a good bet. If I plug in 0, I get f of 0. What is f of 0? It's 3. 1, 2, 3. Okay, that's exactly what I had here. I had f of 0 equals 3. So far, so good. We match so far. What if I plug in, let's say, 2? Well, if I plug in 2, well, half times 2 is 1. And what is f of 1? That's 4. So if I plug in a half, I get 4. There it is. Right? To get 4 in my original function, I would have to plug in 1, not a half, but 1. And then I would get 4. Okay, fine. What happens if I plug in 4 for t? If I plug in 4 for t, oh, I'm sorry, this was not a half. We didn't plug in half. We plugged in 2 here. I apologize. Let's erase this. Let's redraw this. Okay, so we had plugged, so 0, we had 3, 1, 2, 3. And then we plugged in 2, and we got 4. 3, 4, 2, right there. Okay, so what happens if I plug in 4? If I plug in 4, 4 times a half is 2. What is f of 2? It's 5. So if I plug in 4, that's 3, that's 4, I get 5. 5. So that was my 4, that's my 5. There we go. What did I have to plug in the original to get a 5? Well, I had to plug in a 2, right? Because 2 plus 3 gives me 5. So look at what's happening here. When in the original, I plugged in a 1 to get 4. In this version, I have to plug in 2 to get 4. In the original, I plugged in 2 to get 5. Here, I have to plug in 4 to get 5. So it seems as though my function, my line, has been stretched horizontally. It's been stretched horizontally. Okay, whereas before I had to plug in 1 to get that value, now I have to plug in 2. Whereas before I had to plug in 2 to get that value, now I have to plug in 4. And if you try more examples, you see that whereas before you have to plug in 3 to get a 6, Now you're going to have to plug in double the 3, which is 6, right? So you're stretching your function by a factor of 2, the reciprocal of whatever it is, whatever this is. So I will leave it to you to think about what will happen if my function is f of 2t. So think about it this way. If when we had half t, we stretched our function along this axis here. What would happen if now we have 2t? And again, if you're not, instead of a half, we have 2. If you're unsure, again, I encourage you to plug in some points, compare the graph to the original one's graph, and it'll come to you. Let's move on, and we're done. So these are exercises. And his book, he has quite a few. You will notice there are 54 exercises. Unless you have the time and maybe the interest, I do not recommend you do all of them, because some of them repeat, they're mechanical. If you can do 1 or 2, you can do all of them. So pick and choose. I suggest read the question. If it seems like you're unsure about how to solve it, do it. If you read the question and you know for a fact that the steps just come to you immediately, skip it. Okay, so do the questions. When Discord's up, I'll be happy to help. The other guys in the calculus channel will be happy to help. Ask the questions. I suggest you do the exercises, because so next time we'll continue with 1.2. All right, have a good weekend, everyone. See you later.